Hi, this is Larry Benko again. This is the 13th video in the SimSmith Basics series, and I intend for it to be the last video unless there's new features in SimSmith in the future that fit into Basics category. Today I want to talk about several topics which are probably familiar to most people in amateur radio. And let's start with a very simple one, and that is, does open wire line have lower loss than coax? There are people who are adamant about the fact that open wire line is the best thing in the world, and there are people who think it's not so good. Now, to answer a question like that, which SimSmith is perfectly capable of answering, we have to take some personal opinions and stuff out of the equation. We can't look at open wire line versus coax based on cost. We can't look at it based on how difficult it is to put up. We can't look at it based on how well the shielding effectiveness of it is. We're going to look at it just from the point of view of loss. And that's something SimSmith is very capable of doing. So let's start this off with a pretty simple comparison between two types of lines. So what we're going to do here is we're going to put a transmission line in our circuit, and we're going to basically compare these two at the same length of transmission line. So let's make this transmission line on this side be the coax. So let's go find a piece of coax. And for this example, I'm going to compare good quality 0.4 inch diameter coax with open wire line. So let's pick something like LMR 400, which is good quality 0.4 inch coax, and let's make it 100 feet long. Then we're going to clone the load here with a isolation block. Make sure we're cloning the load. We are. Okay. And we're going to put another piece of transmission line here. This will be a piece of open wire line. For it, we will use the generic 600 ohm open wire line. I'm not really sure exactly what that is. It's either 14 or 12 gauge open wire line, but it's got a 92% velocity factor, which is higher than window line is. The window line examples here have velocity factors usually at 0.91 or something, 0.887 for that one. So we're going to use this one. So this is probably about as good as it gets, unless somebody wanted to be really pretty ridiculous in what they were doing. We'll set it to be 100 feet also. Now, in order to be able to compare loss in this transmission line to loss in this transmission line, we need to remove the possibility of mismatch loss. And that's because in an environment where we're going to vary the loads to both of these transmission lines, and we're going to see what the loss is, we need to be able to make sure the generator puts out a constant power into both of these transmission lines so that we can compare the power in the loads. And to do that, we change the generator type to be an X-match type. When we do that, we get the little box with the M in it. These two M's are not the same matching network. This matching network matches this generator to this impedance right here. This matching network matches this generator to this impedance. This generator, clone the generator, matches this generator. So the fact that this is an X-match generator of 1 watt, this is a 1 watt generator also right here. Now what we need to do is we need to pick a frequency range we're going to look at this from. Let's go from we'll do it here. We'll go from 1.8 to 30 megahertz and 0.05 megahertz steps. And if you're not familiar with this command, this is documented in the presenter part of SimSmith. But basically, it's just another way of, we're going to sweep from 1.8 to 30 megahertz and 0.05 megahertz steps. That's all it is. And there's sweep and so on. Now what we need to do is we need to come along here and vary the load. And we also need to look at what's going on here. So let's set our generator, well, it's already set. We're going to look at the power delivered to this transmission line and this transmission line. This one shows as minus 964 atto watts. Basically, it's 0 dBW. This one's 0 dBW too. This one has minus 0.39 dBW out, minus 0.381 dBW out. Let's look at both of the plots here real quickly. So we're looking at the generator over here. We'll look at T1. And T1 looks really small. Okay. There we go. That's a little more reasonable. And basically what we got here is with us, let me change this to something like this. Say with a 20 ohm load here, the coax has a 2.5 to 1 SWR. The 600 ohm line is running with a 30 to 1 SWR. And, you know, it is what it is. And let's go here now and look at we don't need to look at SWR anymore. We'll look at the power in the load and the power at LG1. And there's our two plots. So the red plot, which is the coax, and the pink plot, which is the open wire line. So at 20 ohms for a load, we see that the coax is actually less lossy than the open wire line. The open wire line is worse. If we drop the impedance down, it gets even worse. So the coax is beating the open wire line in terms of loss fairly handily at these low impedances. If we go all the way down to say like about 2 ohms, 2 ohms is a 25 to 1 SWR here, and it's a 300 to 1 SWR on this piece on the open wire line. It beats it at say 10 megahertz by about 2 dB, a little less than 2 dB. So you'd say from this point of view that the coax actually is faring pretty well against the open wire line. Now let's raise the impedance up. Oh, by the way, if we're down here and we also I set this to be a linear increment because I want to go above and below 0 here, and give a hard time doing that with a geometric step size. So if I raise the impedance, you can see it's 1.6 plus J40. The two are getting closer together. And down here, 1.6 minus J40, they're closer together. But at 1.6 plus J0, the coax wins pretty handily. Now let's raise the impedance up again. And as we raise the impedance up, we start to see both of them have lower loss. That's to be expected. The SWR on both these transmission lines is dropping. By the time we get to say 10, let's say we get to about 10 ohms here. At 10 ohms, it's a 5 to 1 SWR on the 50 ohm transmission line, and it's a 60 to 1 SWR on the open wire line. Again, though, the coax is still beating the open wire line at all frequencies, by the way. Now let's go up here a little further. And by the time we get somewhere up here around, let's just say there, around 47 ohms, the two are equal. Sometimes one's a little bit better than the other one, but it's less than 1/10 of a dB. You could say they're fundamentally equal here. If I add some reactance to the circuit, adding reactance makes the open wire line better. Reactance in the opposite direction makes the open wire line better again. As we continue to raise this impedance, we start to see the open wire line really shine. At a 200 ohm, roughly a 200 ohm impedance, whether it's got reactance or not, it's pretty well beating the coax by quite a bit, by at least a dB, about approximately dB when it's resistive, and by more than a dB when it's reactive. Let's continue on up here. Let's go up to maybe like, say, 1,000 ohms. It's somewhere around 1,000 ohms here. Let's just put 1,000 in there, make it exact. At 1,000 ohms, resistive, the open wire line beats the coax by about 2.7 dB at 10 megahertz. And notice how it beats it by a larger amount as you get higher in frequency. As we add reactance to this circuit, it beats it by even more. There's 600 ohms of reactance. Again, it beats it. So, is it true to say that the open wire line has less loss than the 0.4-inch LMR 400? And the answer is clearly no. It doesn't have less loss everywhere. However, let's do one more little thing here. let's change this instead of from me just messing around with this, with values. Let's put a file in here which represents a 132-foot dipole. 40 feet in the air, flat top dipole. Put the impedance in there. Now these two things will track the actual impedance of that dipole versus frequency. And this is kind of interesting. So what we see here, remember the pink curve is the open wire line, the red is the coax. What we see is where the dipole is resonant around 3.5 megahertz, we see impedances probably 50, 60 ohms, and the two transmission lines have almost exactly the same loss. At low frequencies, where the circuit becomes almost completely reactive, it's just maybe like 10 ohms and minus J probably. Well, let's do it here. We can see what the answer is by doing this. 1.8. It's 8.6 ohms minus J, 1.12K. The open wire line has got almost 4 dB of loss, but the LMR 400 has got over 17 dB of loss. You do not want to drive that dipole with coax if you want to use it on 160 meters. Now, granted, it's not a half-wave dipole. It's a half-size dipole, but nevertheless, that's a significant amount of loss. At 20 dB down, you've lost 99% of your power. So this is kind of this is not good. Where 4 dB down it's 4 dB. That's all, that's the best we can do at the moment. Watch what happens here. Any dipole is resonant pretty close on the third harmonic, the fifth harmonic, the seventh harmonic, and that's what we're seeing here. But in all cases, the open wire line beats the dipole, driving the dipole beats the coax. What about on the frequencies where this is not a odd multiple, this dipole is not an odd multiple of half wavelengths? And like 7 megahertz, it's an even multiple. At 7 megahertz, the LMR 400 would have a 7 dB loss roughly, and the open wire line would have about 0.2. At 14 megahertz, that's close enough. It's got 7 dB of loss again. Open wire line's got 0.2 again. On 15 meters, it's got 6.7 dB of loss. Open wire line has 0.196. So it's pretty easy to see what's going on here. If we go back to the Smith chart and we get rid of all the extra noise here, what we see is here's the impedance plot of the half-wave dipole, the 80-meter half-wave dipole. This is all over in the area where the open wire line is much better than the coax, with respect to loss, that is, except for maybe right in here where the two of them are almost exactly equal. So we see over a frequency range from maybe 3.7 to maybe about 3.4 megahertz, which is kind of what we saw here, 3.4 to 3.7. These two had pretty close to the same loss. The open wire line beats the coax handily. So this isn't really doesn't put the debate to bed. You can certainly do this again if you wish with a different type of line. You can pick pick one of the smaller window lines. You can do the graph. Here you see on 80 meters, the coax is actually lower loss than the open wire line by a little bit. But the open wire line is still doing pretty good job over the range. However, on 160 meters, that small window line is pretty lossy. So anyways, this is it is what it is. In the last video, I showed how you could measure the loss in a piece of coax with just an antenna analyzer. If we want to know a little bit more about a piece of transmission line that we get, let's suppose that somebody gives you some coax and you have no idea what it is. What can we do? What can SimSmith do to help us figure out what the surge impedance or characteristic impedance of the transmission line is, and whether it's of any use to us? I've picked up a lot of Teflon coax over the years, and some of the stuff has been like 12, 15 ohm coax made by people like Microdot and stuff, and it's kind of useful for some functions, particularly transmission line transformers for solid state amps and stuff like that. May not be very useful for antennas, but nevertheless, let's look at what we got. Let's suppose we were given a roll of coax, and I'm just making this up now. Let's suppose it's 20 ohm coax, And let's suppose it's got maybe, I don't know, 0.5 dB per 100 feet loss, I guess, I don't know. And let's say it's 0.7 velocity factor. If we bring it home and we don't know what it is, so we're going to put a little 50 ohm resistor, solder a little, say like 06, 03, 08, 05 resistor across here, and we're going to put this into our antenna analyzer. And we're going to use enough of a length of coax here to give us a full revolution on our plot. So what we would do here is, I don't know what kind of analyzer you might have, but let's suppose your analyzer can go up to 100 megahertz. So then we would need to use something that would probably be at least 4 feet long. Let's say 4 feet. It doesn't matter if it overlaps. So what we see here is we see a rotation to the low impedance side of 50 ohms. So we know that this transmission line has an impedance less than 50 ohms. If we'd like to know exactly what it is, it's not the center of this. I think I've discussed that a couple times in videos before. The point where it actually is where this converges to. Well, we can see what it converges to. If I make this line longer and longer, we start to see it converging out here. I see right about there, and we can see that that's not in the center, but it tells us which direction it is. And if you want to know what it exactly is, you can take this number here times this number here and take a square root of those, and you'll be pretty close to the impedance. Or in a case like this where I knew it was down in the 20 ohm range, I'd probably cut this resistor out and put a 20 ohm resistor in there, and I'd see that what I got then was a very tight rotation that was 20 ohms. And if I guessed wrong and I saw that it was say I didn't have a 20 ohm resistor, I put a 22 ohm resistor in there, I would see that the curve started here at low frequencies. Let's do this not as a sweep but as a plot. We can see at the low frequency end, it starts here. It starts there, which is about 22 ohms, and we see as we start to sweep up in frequency, it goes over to here, which is about 18.3 ohms. We can see that's probably 20 ohm transmission line. So that's a really easy way to determine what the impedance of the transmission line is. In this topic, I'd like to discuss the quarter wave transformer. The quarter wave transformer, in most text that you see in magazines and stuff, is basically treated like almost like a magical device, and it's not magical. It's just a basic. It's one specific example of coaxial rotation, transmission line rotation, and that's all it is. It's nothing special. Yet it gets this special treatment a lot of times by people which I think don't really understand it that well. Typically what you say, what the gist of the argument is, if you have something like an antenna that produces an impedance here around the 100 ohm range, and you take a 75 ohm piece of coax and you make it a quarter wavelength long, what you end up with is something near 50 ohms. And we can demonstrate that. And let's demonstrate that with absolute lossless coax for the moment. I keep saying coax, but transmission line. It could be open wire, it could be a window line, it could be ribbon line, it could be anything you want. And we start here at, say, somewhere around 100 ohms, and we make this 90 degrees long. And what we see is, well, we're not quite there. What really is the case is this quarter wave transformer acts as the endpoints being, the geometric mean of these endpoints is exactly the impedance of the line. So for 50 ohms, we'd need 112.5. So we take 50 times 112.5, the square root of that, we get 75. So if we've got 75 ohm coax, this really needs to be 112.5. Let's see what that does. And sure enough, that gets us a very good match with a quarter wave. However, how many people build an antenna that ends up with this impedance? This impedance is 112.5 plus J0. What happens if you built an antenna and it ended up being, let's just say the endpoint was not there, but it was there instead? And again, full wave loop generally is in this range. So things like a one wavelength quad loop, rectangular, square, triangular type delta loops all have impedances in this range, which is why this quarter wave section is used. If I used the standard quarter wave section I did before, I'd end up being here. Oh, actually, before I go too far here, I should mention one other thing. 112.5 is not really the right answer. If we have to coax with a transmission line with loss in it, let's put something like how about Belden RG11? If we put RG11 in there, we notice we're not there. This has enough loss in it that the real impedance where this needs to match is somewhere around 114 ohms, I think. Yeah, maybe even a little bit more. 115. Pretty close to 115 ohms. So now 115 is our target. But as I said before, we were going to drag the antenna that we actually built to somewhere up here. So now what happens? If I want to do nothing else but have a piece of transmission line here to give me the best match possible, well, I sure as heck don't want to stop this at a 90-degree rotation. The wise thing to do here is clearly to extend the rotation up to, say, someplace like there, 103 degrees. That's pretty far off from 90, but that's actually a better match. We can make this match even better if we want to. We can make it better by doing something. Let me see if I can get this right on the first time here. There we go. If I added a capacitor across the antenna points there of 70 picofarads, and then put a 68-degree length of transmission line in there, I'd have a better match. I mean, there's a whole host of different ways of doing this. Maybe you don't want to use a capacitor here. Let's get rid of that capacitor. Capacitors maybe aren't real good weather-wise. Can we put an inductor over here, maybe? No, that's not going to be working that side. Let's put a series inductor here and see how that works. That's going to work just fine. Okay, in this case, 129 nanohenries in series with our transmission line. Now it's 107 degrees instead of 68 degrees. Again, much better match than just using a 90-degree section. There are so many ways you can match this that are better than just putting a 90-degree piece of transmission line in. I'll do one more example here. Let's suppose it ends up being over here somewhere. Instead of being 100 and some number of ohms, it's in this case, it's 85 plus minus J13. So now in this case, I believe we're going to need to after a while, you get to where this stuff is almost second nature. And if you're watching this video and you're saying, well, how come he knows how to do it and I don't? It's only because of practice. SimSmith will give you the same answer it gives me. It just may take you a few minutes longer to get it. In this case, this is one way to match it. It's not the only way. Inductors are nice. You can mount an inductor outside. It can be self-supporting. You can wind it with, heavy gauge wire. It's self-supporting. Across the antenna terminals, would be a good solution. We can probably do it with a capacitor here too. No, we can't. There. Okay, in this case now we've matched it with 50 degrees of transmission line and a 50 picofarad capacitor across the antenna terminals. So there's several ways to match this. Effectively, all of these become basically an L network of some sorts. But it's the kind of thing where don't get all concerned about the fact that it has to be a magic 90 degrees of rotation. There's plenty of other solutions that are actually better. Now, if you happen to build something that happened to end up being 114 ohms here plus J0, then of course 90 degrees would have been the right solution. Another fairly common discussion that happens in the amateur radio community is how bad is the UHF connector? The UHF connector is pretty much ubiquitous in amateur radio equipment. However, there are many people out there who believe that it's not a very good connector to use, and they believe that the N connector is a better connector or something else is a better connector. But let's use SimSmith to see what we can figure out about the UHF connector. I did a bunch of work a couple years ago. It's on my website, w0qe.com, under technical topics about UHF connectors. We made a ton of measurements. But rather than go through that kind of stuff, what I want to do here is primarily to reiterate using SimSmith to show this. So anyways, after I did all the work, I came up with a model for a UHF connector. And there was two models. And I decided I was not going to scrimp on cost. I was going to buy a Teflon male connector, and I was going to buy either a Teflon female connector or a phenolic one. And for this example, let's use the Teflon and Teflon. The Teflon has a characteristic that's different than most other plastics. Teflon and high-density polyethylene are the only two plastics that I know of that have dielectric constants of like 2.1 or 2.2. All the other plastics have dielectric constants above 3, usually 3.4 and higher. The reason this is important is that the center pin in the UHF connector is too large already, and by using a dielectric material that has a relative permittivity that's higher than basically air, you end up with the impedance of the connector, the native impedance of the connector, being too low. In this case, the model for the connector turns out to be a 1.03 inch long piece of transmission line with a 36.2 ohm impedance and a velocity factor of 0.695. 0.695 is the velocity factor of Teflon. And this is a mated pair. It's not very wise to talk about a connector that doesn't go anywhere. So you got to, for every PL259, there has to be an SO239 if you actually want to get any RF to go anywhere. So, and this is not a SO239 barrel connector. This is a SO239 that would go on a panel. Now, if we look at this connector and we plot it versus frequency, and I'm going to sweep it from 1 to 450 megahertz, I get an SWR, I get a Smith chart plot that looks like this, or I can sweep it here. And I see that at the top end of 70 centimeters, we have about a 1.25 to 1 SWR. And that's a number that a lot of people use pretty regularly. And the problem with that is if I stack a couple connectors in a system, I can end up with a pretty high SWR. But since in all connectors, or actually in all transmission lines, the impedance of the transmission line is basically the square root of L over C. What it means is if your impedance is too low, it means either L is too low, the inductance is too low per unit length, or the capacitance is too high per unit length. Well, in the case of the PL259, the capacitance is too high per unit length. However, if we were to come along and take the PL259 and add just a little bitty inductor on the output of it. I'd like to take credit for this, but this is not my idea by any means at all. I ran across this in a radio one time, and I was wondering what the heck was going on. A few years later, it occurred to me what was going on. So anyways, if I add about a little bit less than 4 nanohenries in series with the connector here, I took my SWR that used to be as high as 1.25 to 1 and made it be just a little bit over 1.1 to 1. Turns out a UHF VHF radio that I've got at home does exactly this. It's an ICOM radio. Inside the UHF connector, the female connector, the SO239, is a small trace. And the trace is longer than it needs to be. And I suspect it's just 3.5 or 4 nanohenries of inductance. Actually, if you really want to be even If you want to be even more particular than this, you can increase this value somewhat and put a small capacitor here, and you can see that you can get some incredibly good compensation for this connector. We need about, I think, 2 point something. There we go. We're down now to maximum somewhere like 1.01, 1.02 here. And that may be what the radio does. I couldn't tell about the capacitor because there's a filter there, and I couldn't tell if there was any excess capacitance in the output stage of the filter. But anyways, this is one way to fix some of the problems. But let's look at how good or how bad the connector is on its own merits. So, if we have one connector in a system, and I'm going to put a couple more points here. This is the top of 6 meters right here. Let me put another point here at the top of 2 meters. And zoom in a little bit on here. This is an SWR 1.1 to 1 circle. So on 2 meters, our connector is within 1.1 to 1 SWR. However, if we were to add another connector just like it, let's copy it, Control C, paste it, look what happens. Now our SWR is considerably higher. However, if these two connectors are not adjacent to each other, but they're in between some small piece of cable, which is usually the case, we can see that as we sweep the length of this cable, ignoring the frequencies above 2 meters per minute, if we have about a little bit less than 1 foot between the two connectors, these actually cancel each other out, which is very interesting. Now, they cancel each other out, but and obviously 70 centimeters is not completely canceled out by any means, but up through 2 meters, they cancel each other out. And you can pick any frequency you want. You can do this. We could show this by, let's sweep the length of the transmission line that's in between. Let's go from, say, 0. I don't know how big we need to be. Let's say 3 feet. And let's sweep that. Look at this. Okay, that's good enough. What we see when they compensate each other out, the SWR is almost perfect. When they don't, the SWR is larger than any one of them by themselves. So we look at just one of them. There was SWR for 1, but together they can be better. 2 can be better than 1, or 2 can be worse than 1. And generally, you generally don't try to pick this length. But what it does mean is if you have 3 or 4 of these in a system, the likelihood of all 3 or 4 of them adding up in the wrong direction is pretty low. Anyways, you can play with this in SimSmith, and it shows you what's going on. Of course, the advantages of the UHF connector are a captive center pin, which is something a lot of end connectors don't have. A lot of the new end connectors do have captive center pin, but a connector that's attached to coax, and you take the coax, you heat it and cool it, sometimes the center pin can be pulled out of the connector in an end connector. And that's a fairly common thing that I've experienced in places I've worked in the past. But anyways, this is one of those little topics that people discuss this all the time. With a little bit of effort and a little bit of time making some measurements, you can discuss it from a point of view of actually knowing what's going on rather than listening to somebody tell you how bad it is or how good it is. Because there's certainly plenty of people out there who say, don't worry about the SWR at all, and there's plenty of people out there who say it's atrocious. Anyways, the advantage of the UHF connector, of course, is a large center pin, which is a lot of contact area, which is good. And the other advantage, of course, to it is it's inexpensive. It isn't waterproof, and it isn't constant impedance, but it may not matter to you. Anyways, hope this has been interesting. And for the last topic in this video, I'd like to discuss the merits of using recycled hardline, specifically from the cable TV industry, as opposed to purchasing 50 ohm cable for a long run, say to an antenna or a tower or something. Let's start off by looking and seeing what we can do to use SimSmith to help us put this in perspective. Let's take a 50 ohm load. We're going to take a piece of transmission line. It's going to be 75 ohms. See what the biggest thing we can buy is. Biggest thing we can take out of our catalog here. Looks like LMR 600. LMR 600 is 0.6 inch diameter coax. That's not as big as the cable we might get from the cable TV industry, but let's see if we can adapt this to what we want it to be. Let's build another circuit here with an isolation block. Again, it's a 50 ohm load. And let's take the default transmission line here and set it to have the same parameters as the LMR 600. 0.87 velocity factor, 75 ohms. Let's set both of these to be 100 feet also while we're at it. So we're comparing apples to apples. And let's see, we're going to look at the here and LG1. Okay, we already have the generator type set to be X match, which is needed so that we don't have the effects of mismatch loss affecting the answer. What we see here is that the loss of the simplified model here is much greater than what the LMR 600 is, and our coax is even less lossy than this. So let's drop the loss of this down until we get the two to be pretty close to equal. So something like that is very close to being equal. 0.224 dB per 100 feet. Well, if 0.224 dB per 100 feet is what 0.6 inch diameter coax can give us, 0.875 inch coax is obviously less than that. So I'm just going to define this at the moment and call it 0.2. It might actually be less than 0.2, but then again it's used, I don't know. Let's call it 0.2. So we're going to dispose of this piece, and we're going to call this our free coax that we got. Now we're going to compare it to something that we're going to purchase. Let's purchase LMR 400. And again, LMR 400 has to be also 100 feet. And what we see is we see that the LMR 400, even though it's running within 1-to-1 SWR, has higher loss than the 75 ohm hardline. So that's kind of interesting. So what does that mean? That means we can increase the length of our hardline until we get to the same, approximately the same place here. There we go. So 180, basically 100, let's call it 185 feet. 185 feet of this free hardline has the same loss as 100 feet of purchased LMR 400. Now, what's the downside to doing this? Well, the downside to doing this is, of course, that the free hardline probably does not come with connectors, and it's a function of how long the pieces you get are. Let's suppose you have to splice in the middle and you have to do something at the ends. So you're going to have to come up with connectors, or you're going to have to know somebody who's got, can fabricate something to build a connector or something. It doesn't have to be a connector you take off, but it has to be some kind of a mating arrangement to be able to use this coax. But it might be worth a shot because it has lower loss. So when we do this, we'll see a couple things that are, it's not exactly apples to apples still. Let's look at the Smith chart for a moment. And what we see is the LMR, not the LMR, the 75 ohm cable TV free coax rotates around this circle here with a 50 ohm load. It's got a 1.5 to 1 SWR. It rotates between 50 ohms and somewhere out here 110, 120 ohms. And we don't know what impedance we're going to end up with. Clearly, the impedance we end up with is a function of the length of this and what frequency you're on. So we might need a tuner here. And that tuner that we need might not be needed here. It would be needed here perhaps if the antenna was such that it didn't have very good SWR bandwidth and you wanted to operate in part of one of the bands where it didn't work well. But in general, let's assume that the antenna here is a good antenna and we don't need a tuner. We do need a tuner here. So the first thing we need to do, here's our ending point right there. We need to make our ending point be over here to see what the worst case loss in a tuner is. Here you wouldn't probably use a tuner at all in this frequency. So let's bump the frequency up a little bit here and see where we get. Okay, now we're sitting right here. This is pretty close to the worst SWR. And it's at 15, well, it's called 15 megahertz exactly. Now let's put a tuner in there. There it is. There's our tuner. Now, if we go look at the loss, what we'll see is we'll see that the pink curve, which is the purchased coax, is better now than the black, which is the free coax. So let's drop the length of the black of the free coax back a little bit. Oop, didn't take very much at all. Something like in there is about right. Now notice the two curves don't have the same shape anymore because one of them is running at a low SWR and the other one's running at a higher SWR. And as we saw in the last video, the SWR curve you get fluctuates with frequency due to the high and low loss sections throughout the coax. But nevertheless, the total loss is all we really care about. We don't care if it's divided up into different amounts of loss in different sections. We're not going to heat the coax up and hurt it or anything. So this is what we get. So we can go 1.75 times as far with this free coax as we can with our purchased coax. And you could say, well, I'm gonna spend a little more money than LMR 400. So let's go spend a little more money with it than LMR 400. Let's go buy LMR 500. Now we got to compare it again. Now I can only go 1.336 times as far. Now if I want to spend some more money, I'm starting to spend some serious money here now. LMR 600, it's better yet. Let's keep going. Even with LMR 600, they both have about the same loss now. This is going to cost you a fairly good chunk of change. This is free. It's something you might want to consider. It does mean that you're going to need a tuner here. The tuner probably doesn't need to be variable components. It probably could be fixed over a band, and you switch them in and out. It may not be, may not be for everybody. It may be for some, but it's another interesting use in SimSmith. If I've done anything of any value in these videos, I hope it's to encourage people to try stuff and understand what really goes on. There's so much folklore that exists that's backed by people who really don't know what they're talking about for the most part. And with some reasonable measurement equipment, a little bit of care, and some attempt to understand this stuff, the topics are not magic. They're very well known, and improving your knowledge in a hobby that you enjoy is always a good thing. And at this point in time, I'd kind of like to thank Ward Harriman, AE6TY, for putting up with me to request about him. I don't know. I've requested an awful lot of features in SimSmith that he's accommodated me with, and hopefully this is my way of saying thank you to the community, and hopefully this will encourage more people to try to use SimSmith. It's kind of daunting to use it when you don't know very much about RF to begin with. And then it's so powerful that you can apply the program incorrectly sometimes, not know that you've done it. And this is one of those things that's, anyways, if it's been good, then I'm glad I was able to help. I would like to encourage people to subscribe to the channel. I don't intend to do any more basics videos unless there are some new features in SimSmith that would be appropriate to do in this series. I will be doing other videos that'll be a little more complicated, but a more complicated video of a topic that you're interested in would probably be worthwhile. And by subscribing, you get an email that tells you I produced a new video, and by doing that, you can always choose not to view the video, and nothing's lost. Anyways, thank you again very much. And it's been a lot of fun. This is Larry Benko, W0QE73.